So today we'll be talking about the content of the round 2 notebook. Specifically, we will talk about the artificial neural network, basic structure, activation functions, and cross-entropy laws. So many components of the neural networks been already known from the 50s, 60s. So it's not something really new. And one of the ideas is the concept of the perceptron, which is basically a computational unit of the neural network. So let's go through how this perceptron is working and how to implement, simply implement it in the Python. So let's assume that we have feature vector x with 3 features, x1, x2, and x3, and one dummy feature, which is set to 1. We pass this input to this computational unit or perceptron. And first what we do is we calculate the weighted sum, or in other words, we compute the dot product between the feature vector x and the weight vector w. This is so-called weighted sum, which is denoted here as z. This weighted sum z is then sent to the some activation function. We will discuss the activation functions a bit further, but for now it's just some function that introduce non-linearity to the neuron. The output of activation function gives us our prediction or label. In Python, we can first initialize the feature vector x with some random numbers and set the first feature as 1. In this red box, you can see these randomly initialized feature values. Then we initialize the randomly as well the weight vector w, and we compute the dot product between the vector x and the vector w, which is the weighted sum. I hope this formula is already familiar to you, that we discussed last session. This is basically is weighted sum, which is denoted as z. Then this scalar value z is sent to the activation function. In this case, it is a sigmoid activation function, which is coded in Python here as a sigmoid of z. Basically, what the sigmoid activation function does, it squashes all the input into the range from 0 to 1. Here you can see like a small schematic plot of the sigmoid function, which is shape of S. This is basically how the perceptron working, and this is the first simple algorithm for example, could be used for binary classification task. If we combine several perceptrons together in layer structure, this will be so-called multilayer perceptron, which is basically shallow artificial neural network. In this kind of network, we can see the input layer, the hidden units like intermediate layers, and the output layer, which gives a prediction. So the first question is why we need the activation functions. What is the purpose of the activation functions in the network? To illustrate this, let's take a look at the very simple multi-layer perceptron, where we have as an input one feature, one dummy feature, 2 hidden neurons and one output neuron. But in this case, we will have only weighted sums computations without any activation function. As you can see, the result of the weighted sum is a scalar. And if we plot this as a function, it will be a linear predictor for the one neuron, and as well for the second neuron, also linear predictor with a form like a bias plus weight multiplied on the feature. If we combine this linear function, it doesn't matter what kind of bias or what kind of weight we're going to use, we will always end up with the final linear predictor. You can, for example, substitute these values of zeta1 and zeta2 with these equations and see that indeed it is going to be the linear predictor with a certain bias and weight. What does it mean for the neural network? If we have multiple neurons or multiple units without activation functions, the end model gonna be linear predictor. This simple linear predictor that we discussed last time. And basically, if we have a data that cannot be separated or fitted with the linear predictor, as we can see, for example, here, where one class of the data point is in the center of the circle and another is just like surrounded. So this kind of linearly non-separable data cannot be fitted properly by only linear model. So there is no use of implementing such a huge network if there is no activation function, if there is no non-linearity there. Solely for this purpose, activation functions are used. And as you can see in the same example, we introduce some non-linearity. In this case, it's a rectifying linear unit, which is basically thresholding the input. And by combining this kind of transformed input, we can end up with the complex nonlinear functions, which then could be used for like complex classification tasks. There are plenty of different activation functions. We're gonna discuss only the most common one, the most like known one that we use in the notebook. But as you see in this cartoonish example, there are plenty of activation functions, and each of these activation functions has its own characteristic, its own certain features, and more suitable for certain networks. And people are experimenting with different activation functions, but there are some kind of baseline or standard activation functions that usually used in the networks. Yes, so let's also see how this simple perceptron is learning the optimal weight. Last session, we discussed the gradient descent, the algorithm, iterative algorithm for finding the optimal weight. So let's see how the perceptron, or this computational unit of the neural network, finds or updates the weight. So in this simple example, we have one feature X and one weight W. We compute the weighted sum Z, pass this to the sigmoid function that squashes our input in range of 0 and 1. And that's going to be our prediction Y hat. In this case, Y hat is the same as J. To make the example simple, we will use squared error loss, because it's easy to calculate the derivative of squared error loss. So in order to find the optimal weight, or the way to update the weight, we need to calculate the gradient of the loss function of this loss function with respect to weight. So the easiest way to do it is to first compute the partial derivative of this function with respect to j, because with respect to j or y hat. Then compute next local gradient or partial derivative of j with respect to zeta, and partial derivative of function zeta with respect to w. This is a so-called chain rule, and this is due to fact that, for example, here y hat is not just a simple argument. This is actually a function j. And in the case of function j, this z is also not just an argument, but also in function, which is wx. So if we want to compute the full gradient, we need to compute like a stepwise all the local gradients or the partial derivatives. And this is going to be our full gradient. And we will use this full gradient to update our weight. So we scale this full gradient with a step size, and the current weight, we subtract the this alpha multiplied by gradient from the weight. This is going to be our new guess. If it's a bit difficult to understand, you may think of it as a kind of Russian doll of functions. So you have one function zeta, which is in turn an argument of another function j, and this function j is actually an argument in another function f of w. So it's a kind of stacking this first small doll, then a bigger doll, then a biggest doll, and the biggest doll is our loss function. Then this is called the forward pass when we calculate our prediction and the loss. And then we need to compute the gradient, which is a back propagation or backward pass. And if you want to compute the gradient of the function, you need to start from the first doll, from the loss function, and compute local gradient of the loss function with respect to the local argument. Then you compute the gradient for kind of smaller doll for inside function and multiply it by the partial derivative that we calculated before. And then you move once again and calculate the local gradient for another function and multiply everything together. So the only important thing to take from these all explanations is that our full gradient is dependent on the local gradients. So if you have a complex non-linear function, then the full gradient depends on the local gradient at each node in the network. Why it's important? Let's take a look at the sigmoid function. As I said before, what sigmoid function does, it squashes the input to the range between 0 and 1. You can see this sigmoid function in red, this red curve. Another thing that you may notice that if we have large values, for example, we have large negative value, then our output of sigmoid function gonna be going to closer and closer to 0. If we have large values but the positive one, the output of the sigmoid function gonna be going closer and closer to 1. And you may notice that this is like a flat areas of the sigmoid function. And these flat areas of the sigmoid function will give the gradient, the local gradient of 0. You may see the graph of the local gradient of the sigmoid function in blue. And notice how these tails are going to 0 from both sides. So if it happens that the output of the sigmoid function is somewhere like in the tails, then the gradient is going to be 0. And if you have a local gradient 0, then your full gradient in turn going to be 0. If your full gradient here is 0, you don't have any update of the weight. Basically, your neural network is not training. There is a few more problems with the sigmoid function. You can read it if you go with this link. But mainly for this reason, sigmoid function is usually not used in the hidden layers. It's only used as a in the output layer of the network, because it might be that the signal kind of gonna saturate and the gradient will actually die and there will be no updates. Okay. Let's take a look at another activation function, which is the popular choice for the hidden layer. It is so-called ReLU, or rectifying linear unit. Basically, it's a max out function or thresholding function. What it does, it sets to 0 all negative values of z, or the input, and all the positive values and 0 are unchanged. So you have this kind of angled plot in blue. Once again, if you take a look at the plot of the derivative of this function, which is depicted in red, it's actually step-like plot. It goes like 0 here, then jump, and 1 here. This means, again, that for this region, that is for the inputs that are smaller than 0, the gradient's again going to be 0. And one of the problems that might happen with the ReLU units is the so-called dying neuron. So basically, it might happen that certain proportion of the neurons in the networks are dying, and they are never activated, they are never worked, they never pass any signal forward or backward. In order to overcome this problem, there is a version of ReLU, which is basically very similar to ReLU, but instead of setting all the values, all the negative values to 0, we're gonna scale input to some scalar alpha. For example, in this plot, the alpha was equals to 0.1. And you can see now this leaky ReLU plot is in blue, and all the values which are negative now have this kind of slope here. So this leads to the results that we don't have areas of the unit where the gradient is 0, because if the values of z are negative, then the local gradient will have some kind of small constant. In this case is 0.1, so it's not 0. So summarizing, sigmoid function is usually not used in the hidden layers. It is only used in the output layer. With the softmax function, which we'll discuss later. In the hidden layers, the most popular choices are ReLU, leaky ReLU, ELU, and TAN-H. If you are interested in different versions of this activation functions, you may go to this link here. And also, I made a small widget for the activation functions. It's absolutely not fancy and a bit slow, but if you find it useful, I can post it somewhere. So basically, you can choose here some kind of function, for example, ReLU, leaky ReLU, LU sigmoid, and tan-H. Sigmoid. And it will give you the plot of the activation function, some kind of summary. And you can play a bit with these functions. You will have here kind of two units, neuron 1 and neuron 2. First, the output will be linear. Then you will introduce some kind of activation function, in this case, sigmoid. You can scale then this output of the sigmoid function with some weights and get the final results of summing up of the outputs of the neuron 1 and neuron 2. You can find answer to the quiz question where you had to answer how many neurons you need to build such a certain network. You can try different weights and see that, and there is also bias, and see how this weighted sum of these neuronal outputs is changing based on the weights and the bias. There is also another function which is called gradient. Let's say. So here you will have again linear predictor Z. Then this will be passed to the activation function. In this case, it's a sigmoid. And you will have a local gradient plotted for the linear predictor and local gradient for the sigmoid function, and this multiplication of the local gradient. So in this case, you may see what kind of activation functions have what kind of local gradients, where the gradient is 0, where the gradient is the maximum, and etc. So, and let's go next. So one of the most asked question is how many layers or how many neurons do you need in your network? In reality, most people, I think, first search the literature, choose some baseline model that other people tried, and experiment from that. So you need to go by trial and error. If talking about the theory, there is some theory which defines like theoretically how many neurons or how many layers do you need, but it's a bit complicated area of research. And here you can see the citation of the deep learning book. You can go there with this link. It basically says that the simple neural network with just one single hidden layer is able to represent any kind of function. The only question is how many neurons you need in this hidden layer, which is not trivial question. So in practice, the deep networks works better. So maybe you don't need to, it's not a good idea to take one layer with the huge number of the neurons. It's much better idea to maybe take several hidden layers with a smaller amount of the neurons. And there is one more link where you can read a bit more about like some theoretical discussion on the topic. Oops. So now we have some kind of theoretical understanding how this perceptron, this computational unit looks like, how the neural networks looks like. So how we're gonna implement all this in the Keras TensorFlow. As you can see in this memo, one of the important skills that we need to have is work with the library, because we are not implementing almost anything by ourselves. We're just using the ready-made library. You may find the intro to Keras and TensorFlow here if you're interested. So let's assume that we want to code this specific network in Keras. We have 5 features, vector with 5 elements, 1 dummy feature, 2 hidden neurons, and 1 output neuron. This superscript 1 shows the layer. So this one is going to be layer 1, and this is going to be layer 2. And the subscripts will indicate which feature it belongs to and to which neuron it goes to. So basically all the features in columns are on the connections that goes to the first hidden neuron, and all these features in the second column for the neurons that, for the connection that are going to the second neuron. And the biases are stored in the separate matrix. To implement this network in TensorFlow, first we import the library, initialize the object with the TensorFlow Keras sequential, and we usually we don't need to specifically set the input layer, but just for illustration purposes, first we add the input layer with shape 5 because we have 5 features. We add the dense layer with the 2 hidden units and the activation function relu. And we add one more dense layer with 1 neuron and sigmoid activation function. So how many tunable parameters we have here? We have 5 features plus 1 bias. So we have 6 parameters, and we have 2 hidden neurons. So in total, 12 parameters. And similarly, we calculate the parameters for the second layer, and here it's 3 tunable parameters. So in total, we have 15. We can recheck it from the model summary function, where we have the name of the layer, the shape, and the number of tunable parameters. And we can see that we calculated everything correctly. Another useful function is TensorFlow Keras utils plot model. It's more visual. Sometimes it's just easier to visualize the network in this kind of picture, where we have input layer, hidden layer, and output. If we call model weights, we can get the weights that are currently initialized by the model. Basically, it will return a list. The current list have 4 elements, and the first element stores the weights for the first layer for the 2 hidden neurons. So the shape of these weights is 5, 2. We have 5 features and 2 hidden neurons. So the bias is stored separately in the second element of model weights. And as you can see, it's just a 0. First, the bias is initialized as zeros. The same for the second layer. If you call the third and fourth element of model weights, you will see what kind of weights are initialized, what kind of shape it is. Yes. So now when we know how to implement the model in Keras, we need to decide what kind of output activation functions use and what kind of loss function use. So this is a table from Deep Learning with Python, the course book, which basically illustrates how you choose your last layer activation function and loss function. First, you need to decide what kind of problem you have. Depending on that, you choose the activation function in the output layer or the last layer. And depending on that, you use the loss function. So let's divide this table on 3 parts and go step by step. So classification task, what kind of classification task we usually have? It could be binary. For example, email, is it a spam or not spam? If it's a spam, we label this as a 1, for example, and if it's not spam, for example, 0. Multi-class classification task, multi-class single label. So in this case, for example, you have some kind of images. On the image, you can have only one type of animal. So these classes are mutually exclusive. You can have only one positive class. Usually, the label is in one-hot encoding. For example, if you have 4 classes, you have a vector. Your label is a vector, is an array with the 4 entries, and the positive class is set to 1, and negative classes are to 0. So if we have a cat, for example, the first element gonna be 1, the rest 0, and similar for the others. If you have a task where you, for example, you have an image, and on the image you can have like either all animals or none of them or one or different combination. So it's a multi-label, multi-class, multi-label, if you're more precise. So the idea is the same, to use the one-hot encoding, but now we can have several positive classes here. So let's compare the activation function. Let's say we have some kind of vector that we pass to our last layer or to output layer. We will call this input scores as ith. If we pass this array to the sigmoid function, the sigmoid function will be applied to each element of the array independently. So the result in each row is independent of each other. While if you use softmax function, all the entries of this output of softmax function are dependent on each other. So, and all these values are gonna be summed up to 1. If you compare the output of the sigmoid and softmax function, you may find similarities. For example, we have the largest score for the third element after the sigmoid function, and the same for the softmax function. The next goes the second element, 0.77, and the same for the softmax. The second element that goes is the same in the softmax. It just have different value. And you can see the ranking, the order is kind of similar between the sigmoid and softmax. The difference is that you may see that softmax as kind of amplifying the difference between the classes. So it's kind of trying to put more probability, more scores on one class and less on the others. While in sigmoid, you can have a large values, large scores in many classes. So how we interpret the output of the sigmoid or softmax function? and with which kind of classification problem we use, which activation function. It's quite logical that for binary function we use sigmoid. For the binary classification problem, sorry, we use sigmoid activation function, and we interpret the output of the sigmoid function as the probability of belonging to a certain class. So if we have a high probability, 0.8, we can mark our data point as positive class and say, for example, that this is spam. For the softmax, we use it with the multi-class classification problems where the classes are mutually exclusive. So we want to choose only one dominant class with the higher probability than others. And we assigned the label based on that. So for these purposes, it's recommended to use the softmax function. For the multi-label problem, is recommended to use sigmoid function. And how we interpret the output of the sigmoid function. We interpret it as a probability of belonging to a certain class. For example, the probability of belonging to a class cat is 0.4. So we can say that the cats, if the threshold is 0.5, we can say that the cat is not on the image. If the probability is high, we can say that, for example, the chicken and the dog are present on the image. So we kind of evaluate each class independently and decide. It's like a collection of the binary classification task for each type of the class. So now when we decided what kind of problem we have and what kind of output activation function we're going to use, we need to decide what kind of cross-entropy loss we're going to use. So in Keras, you have at least binary cross-entropy loss and categorical cross-entropy loss. In reality, it's just one loss. It's a cross-entropy loss, which is basically negative sum of the true label multiplied by the log of the prediction. But dependent on what kind of activation function you use, you can derive some kind of form of this cross-entropy loss. For example, if you have a sigmoid function as the activation function, basically what you have only two classes. So one is the positive class 1 and the negative class is 0. So by substituting basically this to the formula, you will get the equation, which is basically a logistic loss. And you can use this for the binary classification task and multi-label classification task. And you might find that this loss is called binary cross-entropy loss. On the other hand, if you have a softmax activation function in the last layer, you can see that the true label for the non-positive class is zeros. So if you substitute all the true labels or y is, you will get a lot of zeros. So in the end, you will end up only with the class which has a true label equals to 1. And therefore, we can simplify this loss to this form where we evaluate only the score for the positive class. And this is basically what is a categorical cross-entropy. So in the end, it's a one function, but depending on what kind of activation function you use, it can be a bit simplified or modified. So I hope now you understand what kind of problem need what kind of activation function and corresponding loss function. So we didn't talk about the regression, but basically in a regression you don't use any activation and you use mean square error loss, which is rather simple case. So this is it for me. So if you have any questions, please, I will